Greetings and welcome, friends. Mr. Waddy here. We were talking about similarities within right triangles the t'other day, and it turns out that if I draw an altitude within any right triangle, it produces a total of 3 similar triangles, like this little guy. Oh, it's adorable. Oh, and this medium triangle, and then the big outside triangle, like that. And as a result, you can then relate short legs and long legs and hypotenuse in all sorts of different ways in right proportions that might help you. So notice it appears as though I know all 3 pieces of information for the big triangle, and it appears as though for this little triangle, I know a long leg and a hypotenuse, and for the medium triangle, I know the short leg and the hypotenuse. So I can actually set this up a whole bunch of different ways. Let's say I work with comparing the little triangle to the big triangle, because I actually don't have sufficient information to compare little to medium. So if I say x over 15, so that's long leg to hypotenuse, what would that be equal to? X was the long leg of the little guy. So I got to compare it to the long leg of the big guy. So that'd be the same as 36 over hypotenuse. 15 was the hypotenuse for the little guy, so 39. What if I started with this, alternative reality? What if I said x over 36? 36 is not longer than 39. I said long leg. Yeah. So the hypotenuse is still always going to be longer than the longest leg. I'm just trying to have the vocabulary so we can describe these things hopefully effectively. So what if I started with x over 36? What's a fraction I could equate that to proportionally? Okay, so yeah, x in the medium triangle was short leg compared to hypotenuse. So for the big triangle, short leg was 15, and hypotenuse was still 39. And then we just solve these however, right? You just do the algebra or the cross multiplying. Am I not clicking on this? There we go. Right, multiply both sides by 15 perhaps. I like having my variable in the numerator whenever possible. So let's see, x equals 15 and 39. 3 goes into both of those. Let's see if I can cancel this out with any skill, who knows. This looks like 3 goes into that 13 times and into that 5 times. 13 doesn't fit into that or that. 5 times 6 is 30 plus 5 times this 30 is 150. So 180 over 13, I believe. Did I get it? Am I done? Am I smart yet? Did I achieve it? I don't know. No response. Okay. Internet will tell me. Find the geometric mean of the 2 numbers. So the geometric mean was set up like this, where I say x over 14 is equal to, 20 over x, where I set up my number that's the geometric mean on the diagonal of a proportion. Geometric mean behaves like an average. I mean, it's a mean. But it's not an arithmetic mean where you just add them up, divide by 2. It's this geometric concept. If I cross multiply here, I would end up having x squared equals, what's that, 280? And then I would root both sides. Root. And the geometric mean is going to be the positive number here. So x is equal to the square root of 280. What goes into that? 2 and 2, 4? 4? Yeah, 4 and 70. Can I break 70 down any further? No? Yeah, 235. Nope. 5, 7. Nope. So that's the same as 2 rad 70 is the exact value of the geometric mean here. And as a type of mean, it is going to be between 14 and 20. What is the 2 square roots of 70? I get 16.733 roughly. Which notice is not quite the average between those numbers. The mean would have been 16, I believe. No? No, I lied. 17? Yeah, up 3 and then up 3. Yep. So, yeah. So it's similar, but not the same. Find the value of the variable. All right, so if you're super good at similar triangles being formed by these altitudes, you can do all sorts of great things. Although it turns out there was 2 geometric mean theorems. And it turns out this one, because one of the pieces of information that I know or am looking for happens to be the altitude, this is the altitude version of the geometric mean theorem, in which the altitude is the geometric mean of 12 and y, the 2 segments of this hypotenuse that it subdivided. So I'm going to say something like, I don't know, like y over 18. No, let's do, I guess y is the bigger one there, huh? Yeah, we'll do that. So yeah, small over this is equal to this over larger one. And so 18 is the geometric mean. So I would have, if I cross multiply, 12y is equal to 18 squared. I feel like I should know that one. 324. And div 12. So yeah, it's the setup that's going to be the tricky part. The altitude version isn't horrible. I think the trickier one is the geometric mean leg theorem. Man, got some mean legs. Look at this. All right. So yeah. So this is a leg. Notice I don't know the altitude. Okay, so for the big triangle, one of the pieces of information I have is the leg. Geometric mean leg theorem says that the leg is going to be the geometric mean of the adjacent segment of the hypotenuse to it. So this 16 is the adjacent not this one, because notice this segment is not touching that leg. And compared to the entire hypotenuse. That's the part that tricks you. This case, they happen to give you the entire hypotenuse. Usually they'll throw this one in there, and then you have to find the total length. So the setup would be something to the effect of 27 over 16 is going to equal... no, wait a minute. 16 over 27. I want to set it up. I like setting it up little over bigger is usually the way that I like to do that. So 16 over 27 would equal 27 is the littler one of that, those two. So 27 over z. And then we could cross multiply 16z is equal to 27 squared. And then, yeah, it's just a matter of setting up the proportion. That's going to be the work for you guys, right? I mean, the algebra, you guys, you're already algebra-buddies. Right, so cross multiplying. So I got 45.56-ish. So I'll change this to a squeakle sign. All right, so I think that's all I had. Is it? Yeah, there it is. All right, thanks for watching, Internet friends. Bye.